Okay, hi everybody. I'm Robert Cluley and I'm with...
Hi, I'm Taspagaslis.
And in this video we want to do a short introduction to the use of lavaan for structural equation modelling or confirmatory factor analysis using some of the data sets that we've used previously in these videos. So specifically we've got a survey that Tassos conducted. This is what the raw data looks like, and we're going to try to now fit a model to this data. Tassos, could you maybe talk a little bit about the difference between confirmatory factor analysis and exploratory factor analysis that we've done, or latent variable modelling?
Yeah, so in exploratory factor analysis, you usually start from the data. You don't know if there are any factors present. You're not sure these factors, which variables they contain. And the biggest difference probably between confirmatory and exploratory factor analysis is that in exploratory factor analysis, all the results that you get are based on the variance. So the larger the variance between the items in exploratory factor analysis, the more factors you will create. While in confirmatory factor analysis, you're interested in the covariation between the items that you're getting. And that's why we call it confirmatory, because in order to base your analysis on the covariation, you need some a priori structure. So you
specify what's co-varying with what.
Exactly. So you need some kind of theoretical basis, some kind of theoretical structure to specify which variables are going to co-vary with which. And then the software will run the matrix equations, and it will tell you if your theoretically proposed model fits with your data or not. And then you can take it from there on any kind of alterations you want to make on your data or on the theoretical model as such.
That's really interesting, because I suspect some of the viewers might be like me, where you sort of assumed that when you're doing a model, that model comes from the data, but it sounds like in confirmatory factor analysis it's the opposite. It's the results describe how well your predictions of relationships actually played out in the data.
Yeah, it's exactly like that. So confirmatory factor analysis, if we are to remain faithful to Yoreskog's initial creation, was always meant to be a kind of a forecasting tool, or a kind of a testing tool to see if your predictions, if your hypotheses hold true. It was never meant to be used as it is used today, where people kind of flirt between exploratory factor analysis and confirmatory factor analysis, but using the CFA covariance method as such. And in fact, because a lot of people were flirting and were trying, they were doing confirmatory factor analysis, but they were actually using it as exploratory factor analysis. In the past 10 years or so, there has been a particular stream of knowledge in latent modeling, where they call for what they call exploratory confirmatory analysis. So it's essentially a combination of the philosophy of the exploratory factor analysis with the methods and the tools of the confirmatory factor analysis, and how you can go back and forth between these two different models in order to try and model your data in the best way possible.
Okay, wow. Well, that's probably a good way to start thinking about then the method of doing confirmatory factor analysis, which is an example of latent variable modelling.
Exactly.
And there's some other ways of conducting those models. So, like, students might have heard the term structural equation modelling as another example.
Essentially, structural equation modelling is no different than confirmatory factor analysis, only that in structural equation modelling you have both x and y variables in your model. So you have both independent variables as well as dependent variables in your model.
Mm-hmm. So there's a predictive element to it, the structural equation model, not just how well does the relationship in the data fit what I thought was going to happen.
Yeah, exactly.
Okay, great. So if we open R again as a way of getting the computer to do the statistics and the mathematics for us, because one of the things that I've seen in some of the reading that I've done is latent variable modelling really goes hand in hand with the increase of computing power, software packages like SPSS and others, which make it easier for researchers to actually conduct the analysis because they don't have to do the maths, and the computer can do it for you. And R, as is the case for most things you might want to do, has a package which has got all the tools that you will need to do pretty much all the latent variable modelling that you would want. And there's two which are often used. So I've already installed them, so I can call them. So one is called lavaan, which is like latent analysis of variables or something. It means something, but that's one that you can use, and that's a tool that's actually going to do the maths of the confirmatory fractional analysis. And then another is called semPlot, which is a really nice little package for visualizing the results of your model. And that's one of the other benefits, I think, of latent variable modelling is you can actually produce a really nice picture of relationships.
I think this is really important to note here that when we're writing for a paper or an assignment, ideally you want the visualization together with the mathematical results. So being able to plot things is really important.
Cool. So the first thing we need to do is get some data. As we have done in previous videos, we'll just call it D for data. And that just saves having to type lots of datas every time. And everyone's time is important. And we use the same code that we've used previously, where we'll tell R that we're going to be using a CSV file, and we'll use this little built-in function called file choose, which lets us select the file we want through a more standard Windows browser. And in this case, we're going to add header equals true. If we go back to the raw data, you'll see when Tassos prepared this data set, the first row is the names of the variables. If you don't tell R that it's got that, or it's got a header, it's going to mess up later on. Hopefully it's not going to mess up now. So we launch that, we select the file that we want, and now we've got an object called D, which has got all of our data in, and because we told it it's got a header, we can use this other built-in function called names, and we've got all the names of the variables we want. So we've got data, we've got the two packages that we need to actually do the analysis. So the first thing we need to do is define the relationships in our model.
Exactly. And I think here, already looking at these variables, we can tell our participants that the file was created to have the ability to model some things, and all the scales that we used were scales that could be modeled. So for example, we have at the beginning 3 items that look at general attitude towards the ad, and that would be one of the factors that we would predict would go well together. And then we have a few items regarding attitude towards the ad, regarding elements in the text and elements in the image. In our case, we are going to put them all together in one factor. We know that they fit together in one factor. We've coded them as text and image because potentially, depending on the data, they might also create 2 factors. In our case, they do fit well in one factor, so we can run a CFA with the attitude towards the ad elements and kind of see how that works.
Yeah, cool. And actually, Tassos had very helpfully prepared if you're okay for me to show, an image of the hypothesized relationships between all of these variables. So the things in boxes are manifest variables, or the items on the survey.
Or the observed variables, some people might call them observed as well.
Okay, and then the things in circles are the latent variables that we think will cause any covariance between each of these items.
If we are to talk a bit about the graph, this is a very standardized SEM plot or SEM graph. The arrows that go away from the latent variables to the items or the observed or manifest variables are the arrows that denote or define the variables that create the latent variable. So these items all lead to this latent variable gives to all of these items. And then we have paths, so from one latent variable to another latent variable, we have straight paths. The direction of the path shows the direction of the predictive hypothesis as well. So in our case, one of our hypotheses is that the general attitude towards the ad people have leads to more or less ad involvement. And then when we have double arrows in one of these paths, that actually shows covariance. So here we also make the hypothesis that the attitude towards the ad, both the general and the specific, these two covariate as variables as such.
Yeah. So, and what we can see here, we'll just point out is, as well, Tassos was talking about how all the items on the, you can't see what I can see, so I'm just thinking where the camera is. All these items here, like add gen, add in text, add image, we could think about them as representing add gen as a latent variable, add in text, and add image as separate. Or we could put these together and think about these as specifics of the ad. And actually Tassos and I have prepped a little bit for this video, although you might not be able to tell, and we've realised that perhaps the model splitting these out as separate latents maybe doesn't work as well as just treating them as one. So what we'll do in this video, and probably the next one, because I bet you this is going to get a long video, is we'll just focus on a little bit of this model rather than building the whole thing, because once you know how to do a little bit, you can do all of it. So we're going to create an add gen latent variable and an add spec latent variable, and we're going to tell the model that we think these two latent variables co-vary. So we'll figure out how to create a latent variable and specify that those latents co-vary. Okay, so it's pretty easy to do that, and I'm actually going to do some cutting and pasting from what Tassos and I prepared earlier, and then we can talk it through. So we actually on a notepad already created the syntax for specifying the model, and actually we'll need to do it differently. What we'll do is we'll cut and paste that. So the first thing you need to do is create an object, and by convention people just call it model because it's your model, and it's just a nice way of keeping track of things, but you could, I guess, call it Tassos or whatever you wanted to do. And it's just going to be literally a text file, so you can work in a text editor like Notepad or even Microsoft Word and just cut and paste it across. And what we're going to do is we're going to say we want to create a new variable called add gen, as we have done here, and we're going to say that it is the latent variable that comprises these observed or manifest variables. We'll then create one called add spec, which has got all of the manifest variables from our modelling. But then we're also going to create a line which says these two latent variables co-vary. So I've just cut and pasted that, but you know you could type it out yourself. So to say two variables co-vary, you have two of these little squiggly lines called tildes, and to define a latent variable from some observed variables, you give that latent a name, and then you need equal and one little squiggly line, and then you finish it off with this quotation mark or speech mark because it was text. And that's it. So now you've got a model, and we should even be able to just like call the model as an object, and there it is, that's all the text. Once you've got the model and you've got the data, we're ready to now execute a confirmatory factor analysis with lavaan. Once you've loaded lavaan, whenever R sees CFA, it's going to think that we're calling this thing in lavaan CFA, so we don't have to do anything more. So we now need to create another object, and again by convention it's called fit, but I think you could call it anything you wanted, but let's stick with the convention. So CFA has to have certain parameters. We have to tell it what the model is. In our case, it's called model. And we have to tell it what the data is. And in our case, it's this object called D.
Yeah.
Lavaan's really clever because it doesn't just need raw data, but can also perform a SEM from a covariance matrix or a correlation matrix.
Okay.
But then you need to do a little bit more work in terms of adding some sample details, which you could look up, Tassos, if you were so interested. So once you do that, we just press enter.
Great.
And now we've got our object, which is our CFA object, and we can start to look at some of the results of it.
Okay.
So let's look up, let's look up an image, shall we first, or should we look up the maths?
Yeah, either of the two is
Actually,
okay.
let's start a new video and then look at the results.